All right, this is a demonstration of CC1, which is what happens when a neuron fires, or the action potential. So to pass CC1, you need to understand what's happening in this graph, which shows milliseconds here on the x-axis, and then millivolts on the y-axis. That's MV, msec. Okay, so what we're doing here is we're recording the voltage on the inside of a neuron. Okay, so you could do that with some specialized equipment. You can stick a little electrode inside a neuron, and you can record the voltage of the inside relative to the outside. On average, a typical neuron is going to have a voltage of negative 70 millivolts on the inside relative to the outside. Okay, and we call this the resting membrane potential, and we say that at this point the neuron is polarized, okay, meaning you have a separation of charge, negative on one side of the membrane, positive on the other. Okay, now this doesn't just happen. There are multiple factors that maintain this neuron's resting membrane potential at minus 70. An important one to understand for this CC is the sodium-potassium pump. Okay, it doesn't look like this. I just depict it like this to keep it simple. But this is a little protein that's embedded in the cell membrane of the neuron. Okay, so there's kind of the membrane, and this little protein, it's kind of like a little protein machine, and it pumps sodium ions, positively charged sodium ions, out of the neuron, while also pumping positively charged potassium ions, or K+, in. Okay, so this also is burning energy in order to do this. This is an active process that requires burning energy in the form of ATP, and it maintains a high concentration of sodium on the outside of the neuron and a high concentration of potassium on the inside. Okay, so we call this the concentration gradient, where there's just a difference in concentration of these different ions on either side, on the two sides of the membrane. Okay, so that's kind of how things are right here. Now it's called the resting membrane potential. I don't really like that term very much because it's not a restful state. As we've talked about, this is burning energy, and it's also maintaining a lot of tension. There's a lot of potential energy stored across this membrane that is waiting to be released. Okay, so sometimes there's some sort of a stimulus that increases the voltage of the neuron. Okay, and really where this matters is in the axon of a neuron. Here's kind of a little cartoon drawing of a neuron, okay, with the soma and the dendrites, and then this right here is the axon, and that's where this is taking place. Okay, so if you bring the voltage up just a little bit, and I draw this dotted line, I'm just going to erase the word millivolts here. We bring it up to just a little bit higher, about minus 55 millivolts. Okay, and that's the threshold for the firing of this neuron. Once we cross this, the neuron will fire. It will fire an action potential, and that looks like this. We'll see this rapid change in the voltage, a dramatic increase, way up into the positives, around plus 30 or so. Okay, and then it comes back down. It kind of overshoots minus 70, goes a little bit below minus 70, and then levels back out. Okay, so what happens here? What just happened? So at minus 55, there are what are called voltage-gated sodium channels that have opened up. Okay, voltage gated meaning that they're gated by voltage, and so they're usually closed. Okay, but they'll open when you reach a certain voltage, and that voltage is minus 55 millivolts. Once you reach that, they will open up. Now remember, sodium is highly concentrated on the outside, and so when those voltage gated sodium channels open, that sodium will rush in very fast. Okay, So you'll get this rapid influx of sodium. Now sodium, remember, has a positive charge, so that sodium coming in will drive the voltage up. Okay? Now, this was polarized, and now this phase we call depolarization. Okay, here. Because we're now moving in the other direction. Instead of negative on the inside, now we're moving to positive on the inside. Okay? Now, there are also voltage-gated potassium channels, and they're going to open as well at minus 55. The only thing is they're a little bit slower to open up. It's just a fraction of a second, a millisecond or so afterwards, but they also open. Now, instead of the potassium coming in, like the sodium did, the potassium is now going to go out. Okay? Remember, it's highly concentrated on the inside, so it's kind of crowded in there and it wants to go out. Potassium has a positive charge. Okay? So all that positive charge leaving is going to drive your voltage back down. We call this the repolarization phase. Okay? Of the action potential. Okay? Now, I mentioned that these potassium channels, these voltage-gated potassium channels, are a little bit slow to open up. They're also a little bit slow to close. So you get what we could say is a little extra potassium that continues to go out. And now we were polarized at minus 70, and now we call this hyperpolarization. Okay? Because we're a little extra polarized, more polarized than we were before. Okay? So if you were recording the voltage here in this axon, you would see this little spike up. And it actually continues to travel down kind of like a wave all the way to the end. And this is how this neuron is going to send a signal to another neuron. And this in turn might fire its own action potential and send a signal to another one. Okay? And that's what happens when a neuron fires.